Today we are talking understanding Wi-Fi requirements for business critical applications. Jim Vada, the floor is yours.
You got me with the beard, and you've got me with the Van Dyke, as that was known. So let me know in the chat which one you like better, and be nice, please. But if you don't know me, my name is Jim Vada. I'm the Chief Wireless Officer here at 7Signal, and I'm a CWNE and wireless network engineer and radio nerd. And today we're talking about application requirements and why they're so important for Wi-Fi networks. And we'll get into the details of some classes of applications. This is really a core concept when it comes to enterprise Wi-Fi. And it's really something that helps, put real concrete answers to important questions around Wi-Fi performance, and what you're going to spend your money on in an enterprise Wi-Fi network. But just to define application requirements, these are the minimum network performance requirements an application needs for an acceptable level of performance. So it's sort of like a threshold. As long as you're above these thresholds, the applications that are being supported will perform normally. And, that's very useful because now you've got a measurable SLA that you can measure quantitatively against to see if your Wi-Fi network is meeting the business's needs or not. We always, Wi-Fi is imperfect, right? There's always going to be some level of problems and performance issues, even in a super high capacity, perfectly designed network. That's just the nature of wireless communications. There's always some level of unreliability, and so end users have issues. They tell important people that the Wi-Fi is slow and it stinks and I can't do my job. And maybe that's true, or maybe it's not. Maybe there isn't a Wi-Fi issue. But being able to measure the Wi-Fi against these real benchmarks helps tell the right story about whether that's true or not. And these, we plug in different parts of the Wi-Fi design, validation, troubleshooting process. So it's really important to know the requirements placed on your Wi-Fi network, so that we're not just kind of going on feelings. We've got some things here that can really directly inform our design and troubleshooting and performance validation. So of course, there's a lot of different applications running on modern networks. And the idea is to combine the application requirements that you have and try to meet the strictest requirement for each application you're supporting. So let's get right into it. So if we look at just typical web browsing, email, and office applications, these tend to be the most forgiving apps. They're not connection oriented, and they can handle some packet loss and latency. They really don't need much throughput. I put 2 to 5 megabits per second here, because this often involves video, right? But less than that is often not a problem. And you can achieve this without, having a huge amount of SNR, minus 70 dBm at the cell edge. And the density of APs is really driven more by capacity requirements, because you can meet these application requirements for a large number of users on a single AP. But these kind of networks are an endangered species. There aren't a lot of networks, especially new networks today, that aren't supporting things like Zoom or voice or other, much more latency sensitive traffic. So this is kind of a blast from the past when Wi-Fi was a lot easier to do. We just needed to get pretty good coverage everywhere, and all our apps would just kind of work pretty well, as long as they weren't, connection oriented like some really, really legacy stuff sometimes is. So that's the easy one. We get more into the things that, we're supporting today, like real-time collaboration apps. Think of Zoom and Teams, GoToWebinar, GoToMeeting, those sort of things where now we're doing real-time voice and video, and we want to achieve the lowest latency that we can. That's really one of the most important requirements for these applications is latency. We're doing video with these, so we do need to consider throughput, 2 to 5 megabits per second in general. And you can see, Zoom has published their requirements here. And Zoom, you can get 1080p video with just 3 or 4 megabits per second, 4 megabits per second. So not a lot. And you get very high quality video with group calling too. And here, one way to think about this is to combine what's required for voice application with a capacity requirement as well. But these, because these are demanding applications, most of them have web pages like Zoom is published here that tells you exactly what your requirements are to deliver this application effectively over the network. And one thing I'd say here is, I care more about the voice performance and the voice requirements than the video requirements here. And the reason for that is if you're in a Zoom call and somebody's video starts to break up or their camera freezes, that's really not a big deal. Maybe their face gets stuck in a funny face or something. But as long as you keep hearing their voice and there's not a lot of delay and you can make out all the words they're saying, the meeting continues, uninterrupted basically. But as soon as their voice starts to break up and you miss a word, or there's a lot of latency building up, and now there's this train wreck, we're talking over each other, and oh man, as soon as the voice part of the call starts to fall apart, then it's really, really painful. So for these, if you need to compromise on things, don't compromise on the voice side of things. So let's define some things that are typical for voice. From the application side of things, we really need about 100 milliseconds or less of round trip latency. And that's end to end. So that's from the client to the AP, across the LAN, out onto the internet, perhaps, and then all the way back. Once we get above 100, some apps will say 150 milliseconds of round trip latency. That's when the latency is so big that we have those conversation collisions where we talk over each other, and sort of that natural dynamic of pausing and allowing people to speak gets disrupted. We also want less than 30 milliseconds of jitter. So we need to have a pretty reliable, stable connection. And we need less than 1% of packet loss. Once we start to creep up above 1% of packet loss, that's when we start losing words and it's hard to understand what someone's saying because too much data is being lost. And, you know, the throughput here is very, very low, 150 kilobits per second per call. So that's, you know, older generations of what, you know, Wi-Fi has been able to deliver that for a very long time, right? We don't need 802.11ax for that, or AC or N, right? For a long time, we've been able to achieve that. But the latency and packet loss are really, really key here. And I'll mention the packet loss. Don't confuse that with 802.11 retries. We can lose some 802.11 frames and retry them. And as long as eventually the data packet that's part of that frame makes it across the medium, we don't have any packet loss, right? We only lose a packet at layer 3 when our layer 2 retries, eventually give up. We've done 8 retries or 12 retries or wherever that limit is. And then finally the station just drops the packet and moves on to the next one. It's only if that payload never actually makes it across the RF that we actually experience packet loss. So to achieve this, you know, we need typically minus 65 dBm at the primary cell edge, and that's a common target in a lot of networks today. Now, it's important here, we want to measure that with the voice client itself, right? Because the voice client is probably a handset, you know, like this, that doesn't have the sensitivity and antenna performance of a survey instrument. So we want to meet that RSSI requirement and make sure that the client itself is seeing that in its own configuration. Probably want to be 5 gigahertz only. You know, a long time ago, voice was sometimes done in 2.4 gigahertz, but 5 gigahertz is going to be, you know, the best here for low latency, for you know, lower retries, less interference, and more capacity. And we need a higher AP density than a coverage only design, partly to keep the SNR high and meet that minus 65 dBm requirement, but also so that we have, you know, better roaming, what I like to call graceful roaming, which is the client's well aware of the next AP it's going to roam to before it's time to roam. So before its signal strength has dropped to that threshold where it's ready to roam, it should already be aware of that next AP because it's heard its beacons, it's been able to probe, and it knows it's close enough to it that it's a good roaming candidate. We don't want panic roaming where a client discovers its next AP sort of at the last second and after, you know, its SNR has dropped significantly. That causes packet loss and call breakup. Usually we want to support 802.11k and V. Those amendments on the SSID that's providing voice, that's going to improve roaming performance for clients that support it. We also want to be able to achieve fast roaming, where we quickly establish a new set of encryption keys with the next AP the client's roaming to. The simplest way to do that is just to use a PSK network, because then we just have a few frames to exchange, no back-end communication with a Radius server, and that could happen very quickly. The most secure way to do it, though, is to use 802.1x, use WPA2 or WPA3 Enterprise, but then use a key caching method like opportunistic key caching or the proprietary Cisco centralized key management, or the standards-based 802.11r fast transition. And you can support a more than one of those on an SSID as necessary. Certainly, I think 802.11r is going to give you the broadest compatibility with different voice clients, and you see that supported more and more, and the proprietary and older methods less and less. We need end-to-end QoS on the network, which is one little bullet on a pretty dense slide here, but that could be there have been very, very thick textbooks written on how to achieve that. So it's a desired state, and something to work towards. And I will say the vendor design guides from the enterprise voice clients are really invaluable. See an example of one there from Vocera, where if you have one of their phones, they have a whole infrastructure planning guide that tells you, here's our validated reference design for being able to achieve good voice performance with our handsets. So they'll tell you what your RSSI minimum might be. Maybe it's -67. They'll tell you what the options are to select on your controllers and APs, and how to configure things, and really give you a lot of kind of a checklist of things that you want to try and be able to check most of the boxes in there to get the best performance, because voice is really hard to get right in Wi-Fi. So Vocera offers that, but many vendors do, Cisco and others that do voice over Wi-Fi, SpectraLink, Volt, and so on. So get in touch with your voice vendor and see if they have a design guide for Wi-Fi that can help you with planning. So let's look at RTLS, real-time location services, where we need the highest density of APs typically. So for this to work, we need several APs to be able to hear clients with a pretty high SNR. And in this case, it's 3 or more APs at -70 dBm. So that's a lot of coverage, and it's going to result in some co-channel interference. It's one of the compromises you have to make if you're using Wi-Fi for RTLS, at least the way it's usually been done. Not talking about, say, new things like 802.11 fine timing measurement, which are we're seeing more and more support for that, and hopefully one day that'll replace the need for this. But this is kind of your traditional RTLS, and you got to run it in both bands, and you got to have a lot of 2.4 gigahertz radios enabled, more than you'd want to do, right? To which would typically, you disable a third or more of your 2.4 gigahertz radios if you have a 5 gigahertz design, to limit CCI and all the management frame overhead from those extra radios. With RTLS, you end up turning a lot more of those back on to be able to do locationing and 2.4 gigahertz. We also have requirements on where you're going to place your APs. So, a great rule of thumb with AP placement is put your APs where your users are. If you have a conference room, have an AP in the room. If you have some auditoriums or cafeterias, those places where people congregate, put the APs there in the room with a line of sight. So those Wi-Fi clients have the most SNR possible, and we better serve that high density use case in those areas. Well, now we have to compromise if we're doing RTLS, because we need to put the APs around the perimeter of the floor that we're supporting. Now, of course, we can also put APs in the center as well, but we need them around the perimeter, again, for that triangulation to be the most effective. And so we end up with a higher AP density than even a typical voice design to be able to support triangulation. And here again, this is where vendor design guides and validated reference designs from the AP vendors are really useful. Cisco and Aruba, I know both have published documentation on this. And these are also proprietary technologies. So you really are leaning on the vendors' design guides to make this work. It's going to be a little bit different for every vendor that does it. So use those when you're considering doing this. So let's look at VDI, so virtual desktops. And, this is something that's also growing in popularity. Even though this technology has been around for a while, we see it certainly among our customer base growing, and a lot of customers deploying iGel OS and thin clients and running, Citrix and VMware Horizon and so on, to deliver applications in the most efficient way, but also to BYOD clients and work from home clients and so on. So requirements here, they tend to be a little bit application specific. So Citrix and VMware might have some differences, but in general, this is you can think of this as sort of a light real-time application. We want to have low latency and low jitter and low packet loss, although, there's a little bit more tolerance here, and we're using, pretty strong video codecs to compress the data that's going back and forth between the client and server. And, surprisingly, these don't require a lot of throughput, 100 kilobits per second up to 1 megabit per second for the highest quality. These applications are really network optimized. They use strong encryption methods compression methods and encryption as well, of course, to reduce the load they put on the network. So you can think of this as, having, if you're achieving voice level application requirements, these apps are going to work just fine. And then you want to consider, some modest capacity requirements here too. And just like other applications, these will have, published requirements too, like you can see here for VMware Horizon 7. So let's have a look at high density. And this is, a very closely related topic to application requirements. But this is where we're thinking about not just a single user and what they need in terms of throughput for an application to perform well, but how do we can we deliver that level of throughput to many users in a confined area? This is where doing some capacity calculation, some napkin math is really useful. And there's some interesting discussion about if capacity planning is even uh, possible at WLPC this year. I think it's something that you can get a very, very rough idea with, and you can definitely figure out if you aren't able to deliver the capacity required. But these estimates are not highly accurate. So take it with a grain of salt, right? Because the way we think about it, and you can see here an example from Ekahau Site Survey, which is a really wonderful design tool. And this is absolutely what I'd use for doing some capacity estimation. But what we're specifying is, okay, how many total devices are going to be in an area? What's the throughput requirement for them? What are the device capabilities, right? If the clients are only 1-by-1 clients, that limits the throughput they can achieve, and also increases the airtime they may be consuming, which is an important capacity consideration. So we can kind of put all these things together along with the application requirements and see, are we able to achieve, or what do we need from our design to be able to achieve these requirements for all these users at once. But what we find though in the real world is applications kind of are very, very bursty. Even video applications tend to be bursty, and we often don't have every single client in an area accessing the medium at the exact same time, requiring that same amount of throughput at the exact same moment. Even when there's actively users engaged with an application, right? They're reading what's on the screen, they're thinking about what to click next, they're typing in a form, and then they click and something happens and we need throughput. And that doesn't happen for everyone at the same exact moment. And I mentioned video. That's true of streaming video too. Most streaming video, it's not exactly streaming. It's more like the client's downloading big chunks of a video file into its buffer. It plays through, the first half of a chunk and says, okay, I need more video because I'm halfway through here. And then it downloads another chunk. So it's ready to, and waiting in its buffer. And so, that's something that, again, doesn't happen for every single client at the exact same time. And, my approach to this is sort of, and this is a typical design approach, right? Within the constraints we have, the budget and design requirements, the aesthetic concerns, the installation options, and so forth, I just want to maximize the performance of that WLAN as much as possible, even above and beyond the minimum requirements here. So what I do then with capacity planning is try to go back and see, well, given these very rough estimates, am I still, do I have enough headroom here with some significant margin for error to think this is going to work? Important point there. And like the other considerations, the AP vendors have high density validated reference designs that I would absolutely suggest you have a look at. There's a lot to learn from those as well around Wi-Fi capacity planning. And okay, so, I kind of alluded to this, but application requirements are just one part, one consideration in the design process. We also have to think about capacity. What are our requirements for capacity? We also think about the clients we're supporting. What are their capabilities? What's their roaming performance? What's their what security suites do they support? An important concept here is the LCMI client, the least capable, most important client. So if your voice handset is a 1x1 802.11a radio, that's your LCMI. And you have to design with it in mind, because it's got the most important, or we'll say the most demanding application on it. And it's got kind of the least capabilities, perhaps, of your clients as well. Aesthetic concerns, right? Sometimes the requirement is, I don't want to see any access points. I don't want to see any ugly antennas anywhere. Okay, well, there's a trade-off there, and that is a trade-off in potentially requiring a greater density of APs and accepting some performance costs as well. Power, right? Can we get the PoE that we need, or the mains power for our APs? Backhaul, do we have gigabit Ethernet available wherever we need it, or do we have to think about doing mesh backhaul or long fiber runs or other options? Budget is of course, probably the most significant constraint that we've got. Can we build and design a network with the available budget that meets all the application and capacity requirements that we have in the network? And there's more, right? There's more, and all these things are different puzzle pieces when it comes into Wi-Fi design and evaluation. So application requirements are really important, right? Because they kind of tell us if our constraints are so strict that actually this isn't going to work. If you want to do voice on a shoestring budget with 2.4 gigahertz only APs in a noisy environment, well, that just doesn't work, because this is what voice requires. And let's, we've got to have some give and take to make things work. If we don't know our application requirements, we just design the best 2.4 gigahertz network we can within those constraints, and then everything falls apart, and we have problems. So important point to consider. All right, so after the design is done, I think I might steal a little bit of Eric's thunder here, so apologize for that. But we can monitor with our Sapphire Eye. I'm putting my sales engineer hat on here really quick, but our Sapphire Eye does SLA reporting, so we can plug in all our application requirements into the configuration for Sapphire Eye and say, here's our strictest throughput requirements, our strictest latency requirements. Here's the VoIP MOS we need, packet loss, and so forth. And then the Sapphire Eye will go out and 24/7 monitor that and report on if we're meeting those application requirements or not. And if we're not, we'll get an ugly report with a big orange column like you see here for the downlink MOS in this particular network. And then we know, okay, we need to go in and see what's going on. And similarly, in Mobileye, our software agent, we can plug in our application requirements into the thresholds of our configuration. So we can say, okay, this is the throughput that we have to deliver to our clients. Here's the signal strength they need to get, and so forth. And then we can measure that and see when clients are outside of those SLAs, as measured on the clients directly. So we kind of remove the ambiguity of, is it fast enough? Is it too slow? The client, somebody complained. Is anything really wrong? Well, let's go look. We've got some defined measurable performance requirements. And now we can see on that client if it was meeting those requirements or not. Okay, had to get that in there. So this is an iterative process. And especially it's iterative in, networks that are open to BYOD clients. Thinking of higher education client networks, especially, and also, large stadiums and arenas. In colleges, students are bringing brand new clients in every semester. And they're, last year they're running Snapchat, and this year they're running TikTok. I'll get off my lawn, but they're going to do what they're going to do. And we have to kind of reevaluate things whenever there are these big changes in application usage. Of course, this happens in the enterprise too, but hopefully it's a little bit more of a controlled process with a little bit of warning in advance that, hey, we're upgrading to the next version of Citrix and the application requirements are now, X, Y, and Z. So we need to think about this on an ongoing basis. When new applications come into the network, let's have another look at the requirements. Do they change anything we need to do with our Wi-Fi design? If so, then we need to go through a redesign process, implement and validate those changes, and then start the whole thing over next semester. So, that's something that we're always thinking about, and something that deserves a periodic review. Okay, so that's all I have, and I think we might have a little bit of time for Q&A. A nice comment there from Joe Clark. He says, it's cute you think application owners know what their requirements are. Yeah, I hear you, Joe. I mean, hopefully you just know, you get wind that something's changing with some application, and then you can find those published specs on your own. But yeah, it's uncommon for them to actually know if something significant's changing with specific requirements around there.
What do you do? All right, Jim, yes. We've got some questions for you. So let's take a couple of them. So we've got one from Olivier. Would fragmentation in the tunnel between the AP and the controller affect Zoom performance?
That's a good question. I think it would, if it's excessive. If particularly like if there's an MTU problem and it's, like a constant issue, I would expect that to cause a problem. And anybody that has insight into that, drop something in the chat for us too, if you experience that.
All right. So Feng asks, for voice, are there any clients and APs transmitting voice packets with WMM voice priority?
I like that the way that you asked that, Feng. Are there any at all? Because it seems like there are fewer and fewer. QoS is so important for voice performance, particularly in busy networks. We really rely on QoS over the air to be able to prioritize those voice packets. So the answer is yes, but they tend to be just those enterprise voice clients, those dedicated voice handsets from Zebra and SpectraLink and Ascom and so forth, Cisco, that will reliably apply those WMM voice priority tags to their frames. Now, APs will usually, trust the DSCP that they get from the route switch side, and then apply a matching WMM tag to it. But they can also do application recognition and tag packets appropriately as they see fit. One of the big problems, of course, with end-to-end QoS is so much goes out over the internet now, where all those QoS tags get stripped. So we really rely on things like AVC and so forth to recognize applications and tag them appropriately, so that at least over the air, where QoS is really the most critical, in my opinion, it works.
Mm-hmm. All right, so we probably only have time for one or two more, and they just keep coming. So I don't know, Jim, if you have any preference towards one or the other. Let's see. This is kind of a follow-up to what you were talking about in education. So Rob's asking about what would the typical device requirement look like for public Wi-Fi in an educational environment, and is there best practice?
Yeah, good question, Rob. And I've been there myself. It's public. Okay, so I'm going to assume you're talking about managed devices that the educational environment is purchasing themselves rather than BYOD. But I would say they need to be 2 spatial streams. They need to be 802.11ac, and they have to support 5 gigahertz. If they're AC, it must support 5 gigahertz to be AC compliant. And then I would say, must support WPA2 enterprise as well. And if you can check all those boxes, you're in pretty good shape. And if it's BYOD, again, I like to say, 802.11ac as a requirement, even though 802.11n is actually pretty good from a performance perspective, you run the risk of getting clients that are 2.4 gigahertz only, and end users can't figure out what bands their client support. So just say 802.11ac, and you've got clients that support 5 gigahertz.
All right, we have time for just one more, so I'm so sorry, everyone. Jim is very popular, but let's take this one from Andrew. How similar in requirements is VDI to Windows RDP, VNC, or other desktop sharing programs?
Yeah, very, very similar. RDP is going to be pretty closely in line with what Citrix and other VDI vendors offer. And then VNC, probably pretty close. I think, in both cases, RDP and VNC, you have some options to control the throughput requirement. So you can change, the maximum resolution, and you can change the bit depth of the color bit depth, go to millions of colors instead of billions, and suddenly you've saved a huge amount of throughput. So those are, things you can do there to tune those, particularly if they're, you're using the public internet for those, but very, very similar requirements.
Awesome. Well, thank you, Jim. And sorry we couldn't get to everyone, but when you get that follow-up email tomorrow, if you want your question answered, or if you think of one over the course of the next 12 or so hours, do reply to that. I will receive it and make sure that your question gets answered. But thank you all for your questions. Thank you, Jim, for your answers, and for a great session. And now I think we're ready to roll into 7 minutes with 7 signal. There's Eric Muley. Hey, Eric, how are you?
I'm doing great. How are you guys today?
Doing swell over here.
Awesome.
Whenever you're ready to take it away, let's
Okay,
do
here
it.
we go. It's time for 7 minutes with 7 Signal. This is where we take a little feature inside our products. We unpack it for you and show you how it can have a huge impact on your environment. Now, Jim Vada, of course, spilled the beans a little bit, but I guarantee you that we're going to see a lot more in our 7 minutes together that you're going to love and enjoy particularly. So let's go ahead and do a little sharing here. Ba-boom. And away we go. There you have it. Just give me the thumbs up if you can see that, guys. All right. All right, so here it is. Here's that SLA chart that we were talking about a moment ago. Guys, so we've got these, performance targets that we set. How do we know if we're complying with them? When somebody says, hey, we're not meeting our service level, how do they know? How do you know? Well, we can put a Sapphire Eye in an environment, and all the while it's measuring the Wi-Fi experience. It's determining, are you compliant? And as you can see here on the screen, let's take a look together. These are some of the Wi-Fi experience indicators, and we're determining what percentage of the time are we meeting or beating our target for good performance. So these percentages don't make much sense unless you know the target. In order to see that, just click on the box. So as you can see so far today on this network, this is the 7S Corp network on the first floor, 5 gigahertz. We've done 139 throughput tests already. We're doing them every, kind of in round robin fashion, testing all of the access points in the area. We're averaging 129 megabits per second. Okay, here's the key. Our target is set at 5 megabits per second, just like what Jim was talking about a moment ago. Look, when it comes to just being able to do the hardcore things that we need to do in order to get our job done, 5 megabits is the absolute minimum. And so what I expect is to be in the green as close to 100% as humanly possible with regards to meeting or beating this target. And I've got it for all of these things here. Here's ping round trip time. Again, I want to make sure there isn't any latency on my network. And you can see how aggressive we have that target set here on our network. Let's keep going. Let's look at packet loss and jitter. Packet loss, jitter, here we go. So again, we've set a target for packet loss of 0.5%. And you can see out of 276 samples where our average is. So we're looking really good. Same thing with jitter. We've set an aggressive target of 10 milliseconds of jitter in order to ensure that our people are having really good voice conversations when they're at corporate. And again, you can see what the maximum was and what the average was. So this is just a tremendous way to prove to the business that you're holding up your end of the bargain, and that's what an SLA is, a service level agreement. You and I, we agree that we're gonna deliver a certain level of performance to you, and I've got the evidence, I got the proof to back it up. Now let's take a look at Mobileye, because from the device's point of view, we get some really rich metrics as well from a Wi-Fi experience standpoint. So let's take a look at that right here. So I'm looking at somebody's laptop. And again, I need to confirm that they have good, fast, efficient access and to key resources that I have specified for my network. For example, meet.google.com. Are you able to connect all the time like you should? What's the latency? Same thing with Teams. Okay, so you can see here from the device's point of view, are you able to get to Teams? And when you are able to get to Teams, what's the latency? And I can use this little tiny piece of application performance management in order to decrease the mean time to innocence, if you will, when people say, hey, it's the Wi-Fi network. Well, wait a minute here. From your device's point of view, I've been able to determine that the Wi-Fi is just fine. Look at these key performance indicators down here. You've got, for example, a good signal strength. You got a great data rate. And as a matter of fact, when I look at some of these Wi-Fi experience indicators here, what we have potentially is a Teams problem or a Cerner problem or whatever the application server is that you're confirming connectivity to. Okay. So not only do we have that for ping, we also have it for throughput. Again, from your device's point of view, I want to continually be measuring, okay, is it fast? Is it slow? And you can see right here, both upload throughput and download throughput. I can confirm from your device's point of view that you are achieving the target for good performance. And then once again, let's take a look at voice. We are putting UDP packets on the network, which are stateless, and we're measuring, okay, the packet loss and the jitter accordingly to confirm that we're having a good voice over Wi-Fi experience. And again, here you have it. So we're calculating a MOS score, or mean opinion score, characterizing the quality of the voice conversation over Wi-Fi. And I do that with my packet loss and jitter here. And you can see how awesome, in fact, it looks. So there you have it, guys. That's what I have for you. I wanted to share with you how you use 7Signal in order to confirm that we're meeting the performance targets set by the business. So guys, I just want to remind you, we can't see or hear Wi-Fi, but 7Signal can. Thanks for joining us this week, and have a great one.